electric field. One is obviously going to say that given a charge distribution, I am just going to do this. E at r is going to be 1 over 4 pi epsilon 0 integration dV rho r prime over r minus r prime, r minus r prime cubed here. Is this how I am always going to calculate it? Suppose I ask you a different question. Suppose I go to a region of space here, where I do not know about this charge, but I know field at these points. Let me make it with a different color. Suppose I know field at this point. So what I'll say is field given at a boundary. I do not know about the charge distribution, but I do know field about a boundary. Can I calculate field out here in the rest of the space? Let's look at an example. Suppose I do not specify the charge, how much charge a spherical body carries, but what I give you is, I hide that spherical body, I give you that on this surface the field is all the same on this spherical surface and its magnitude is given by some constant. Can I calculate the field in the rest of the space? In this case, it's very easy because you're going to take the center of the red sphere. You're going to say that E at the surface is obviously 1 over 4 pi epsilon 0 because it's all spherical. Some charge inside divided by r square, that's the magnitude, and therefore E farther out is going to be 1 over 4 pi epsilon 0 q over r square, which I can write as 1 over 4 pi epsilon 0 q over r square times r square over r square. I have multiplied and divided by capital R square, which I am going to say E r times r square over r square. So here I could argue, because of the nature of the field, because it's all spherically symmetric about a certain point, so I could sense that this is due to a point charge. But what about if I am given the same surface, but field is has arbitrary direction, arbitrary magnitude on this surface? What would I do then? Then obviously what I need to do is take the field out here and using some sort of a differential equation, find out what it is at next point, and then keep integrating. So starting from a boundary, one can find field everywhere else if differentials of the field are known. All right. Now, I already said why do we want to do that is that not necessarily every time I'll be knowing what the charge is somewhere, right? I may be given a boundary and where I know the field. How do I build it up from here? So if I know the differentials, I can do that, right? In other words, what I'm saying is, does E satisfy a differential equation that can be solved to find the field starting from a boundary. Where it is known. All right, is that point clear? So what we are doing is we are trying to find a differential equation so that if I know field in on a certain boundary in a certain region, I can build it up from there. Now let us see how many differentials are there. E has 3 components because it's a vector quantity. We have Ex in x direction, is y component, and Ez. And these are all functions of x, y, and z. These are all functions of x, y, and z. X, y, and z. So if I am going from point to point, if I am going from this point to this point, this point, this point, right, all 3 components, Ex changes as I change x, but keep y and z fixed. That means I am taking a partial derivative with respect to x. Ex also changes if I change y, or Ex also changes if I change z. And so do all the other components, right. So if I am at this point, let us say this is x, this is y, this is z. If I go from here in the xz plane, the Ex component may change as I move here. If I go in the y direction, Ex component may again change. So that is described by these 3 differentials, partial derivatives. Similarly, y component will change with all 3 coordinates, and so will the z component. So in principle, I need all these 9 differentials, 3 for each component, in order to calculate field at some other point starting from its value from a given point. So 9 components. And I should be listing all of them. But we are fortunate. There is a theorem, and I am going to say it without proving it. There is a theorem called Helmholtz theorem. And what it states is, given a boundary, suppose I know the perpendicular component of a field, any vector field at the boundary. So perpendicular component of the field is known. Then, and I am going to define and explain those quantities later, if we know the divergence, and I will explain its meaning in a minute, which is the combination of the derivatives in this form, if the divergence, that is sum of the x component derivative with respect to x plus the y component derivative with respect to y and z component derivative with respect to z, if we know the divergence and another quantity called curl. If we know these 2 quantities, all right, let me write its components. For example, the x component of curl would be partial Ez by partial y minus partial Ey by partial z. Y component will be partial z of x minus partial E z by partial x, and the z component is going to be partial Ey with respect to x minus partial Ex with respect to y. If I know this quantity, the curl, and if I know the divergence, I can calculate field everywhere. So let us, this is Helmholtz theorem, and if I know the perpendicular component on the boundary, then I need to know only the curl and the divergence. Let us understand the meaning of these. and that is what the rest of the lecture is going to be about. Today I am going to focus on divergence. Of a vector field. You've heard the word divergent. Divergent means, oh, we say views are diverging. Oh, there's diverging light rays coming. All right. So what basically it means is, particularly because you may have seen it in your 12th grade book, if light rays are going away from each other, we say light rays are diverging. If people have differing views, we say they have divergent views. But for electric field, we are not going to be interested in this. What we are interested in is this diverging mathematical quantity. Light rays are diverging. I could very well replace light rays by a vector field and say these are the lines representing vectors of this field we are considering. Okay. But we want to get a view of what, a feeling for what this divergence means and define it in a very, very precise manner. When we say something is diverging, an example to define it would be a fluid flow, which I talked about earlier. So let us say this water or a fluid is flowing, and all over the place it has a different current at different points, and looks like light rays diverging, this velocity is also diverging. Can we understand what this divergence means? Can I give it a definite meaning? So let's see, if I take a volume, a small volume here, if whatever that fluid is coming in and whatever is leaving is equal, so suppose fluid coming in is equal to fluid going out, in that case I would say it's not really diverging. Whatever comes in goes out, right? On the other hand, if fluid going out is greater than fluid coming in, I will say it's divergent. The fluid flow, the velocities of the currents are divergent because they take away much more than they are bringing in. Or on the other hand, if fluid going out is less than fluid coming in, I'll say it's convergent. I'll say it's convergent because that is like negative divergence. Let us see if it makes sense. Let's see light rays from a lens which I say are diverging, right? And if I take small volume here, in that case, whatever light comes in, right, is also going out. It may not be divergent, but on the other hand, if I take a source of light, a point source of light, and light is going out from here all around. If I take a small volume around it and see the light going out of this volume, all over the light is going out, right. So, this is really divergent. On the other hand, if I take a point here where all the light is coming in, then I will say this is convergent, and it's converging to this point, is diverging from this point. Here, at this point, there is really no convergence or divergence. There could be, as we just discussed, divergence at this point, because everything is coming out of here. So, this kind of gives you a feel for what divergent behavior is. Divergent behavior is going to be when everything is going out, right, or if there is a net outflow, or if there is a net inflow, this negative divergence, or something going in.